Welcome back, everyone, to day 2 of SYCO11. We have our second invited speaker, and I'd like to introduce Morgan Rogers, who will speak to us about endomorphisms of models, yet another categorification of model theory. Take it away.
Thanks very much, Bryce. So, good morning, everyone. If you're feeling especially awake and observant, then you'll notice that there is a slight difference between the title on this slide and the title that was on the website. Just 3 letters different, but essentially what I realized in doing the research for this talk is that it's easier to present this result for monoids than for groups. But if groups are what you really care about, then I do have a slide after the end credits which explains how to adapt this to recover the motivating group theory version. All right, so here's the structure of my talk. First, I'm going to motivate it, in particular, give you the model theory result that I'm going to be extending, and summarizing what the end result is. And then we'll get straight into the topos theory, which I know that you're all really excited about, but just to ease you into it, because it's first thing in the morning, I'm going to give you 4 different ways of thinking about toposes. And I'm going to try to avoid assuming too much. Hopefully at least one of these ways of thinking about toposes will appeal to you. I'm also not going to go into much technical detail, so you won't necessarily come away from this talk being able to manipulate toposes in the way that I'll present later, but at least you should have a general understanding of the pathway of proof that I end up presenting in the second main part of the talk. All right, let's get started. So here's a result from Model Theory by Wilfred Hodges. It's quite an established textbook in the field, and this is from a chapter about automorphisms of models, hence the adapted title of the talk. And what this result says is if I take a set, then I can equip the automorphism group of that set with a topology, such that the closed subgroups of my automorphism group, or more generally, if I take any subgroup of my automorphism group, it will inherit that topology, such that the closed subgroups correspond to the intersections of the original group with the automorphisms of extensions of that set by relations. So I just have a plain set, and I can exchange any pair of elements and exchange any number of elements I like with the full automorphism group. But if I equip my set with some family of relations, and I just look at the automorphisms which respect those relations, then I get a subgroup, and I have this Galois connection between subgroups on the one hand and families of relations on the other. All right. So here is the extension of this result, which we'll get to by the end. And actually, I don't need to present more than the slide for the basic content of the result that I've actually written down to be proved. Okay. This is saying if I take a model of any theory whatsoever, if you don't know what a theory is, we'll get onto that shortly, then I can do exactly the same trick. I can look at its automorphisms, or in fact, endomorphisms. I can take a submonoid of that. I can look at the relations which are respected by those endomorphisms, and I get some family of relations. Or in the other direction, I can take a family of relations, and I get a submonoid of elements which preserve that. So, okay, if I don't need any of the stuff that I'm going to talk about later to actually present this Galois connection, then where am I going with this? The point is that I didn't include the definition of the topology here, but there is some topology involved, and it's not really clear where that comes from. Like, the way this result is proved is Hodges introduces the notion of closed subgroup before introducing topology, before introducing a topology on this group. Like, he defines closure in terms of this Galois connection, and then just presents a topology such that the notions of closure coincide, right? In particular, there's not very much insight into why this is the right topology to consider, but as soon as you have it in hand, you can work it out for yourself that, this works. So the point of this talk really is to show where you might get this topology from, and how it expresses a connection between two different ways of viewing toposes. All right. So now for some caveats, disclaimers. This is work in progress. I was supposed to do the automorphisms version, like I mentioned before. Ask me about it later, and I will guess. You arrived just in time for us thinking about toposes. So, if you've never met toposes before, and you're here at SYCO, which is a fairly category theory focused conference, then you're welcome to just think about toposes as very structured categories. We've got all the limits and colimits that you could want, as long as they're not too ridiculously big. And you've got some other bonus stuff, like being Cartesian closed and having a sub-object classifier, and if those words are meaningless to you, it won't matter. However, while that's technically what they are, there are a bunch of different ways of both building and viewing toposes. And I'm going to spend the next 16 slides or so explaining some different ways. And I will use all of them in the proof in the second half of the talk. So consider that the quiz for how well you paid attention to this first part. So first of all, the definitional way of building a topos is to take a site. I'll tell you what one of those is in a sec. And an object in my topos is a sheaf on that site, some structured data associated with this presentation of my topos. Now, a special case of that turns out to generalize in a different direction is to think of an object of a topos as an action. That is, I have some data, and I have some transformations of that data. There's a logical perspective, in fact, several logical perspectives, but this is the relevant one for this talk. So we can take a logical point of view on toposes and identify a relationship between them and geometric theories. So the geometric will also be explained later, but the point is there is quite a large fragment of logic that I can understand better or appreciate using toposes. And finally, toposes are themselves objects of a bicategory. So even if we completely ignore the internal structure of a topos, we can extract some categorical sounding characterizations of transformations between them. And here grayed out is a fifth way which I won't actually be using besides in illustrative examples, which is toposes as generalized spaces. So I can build a topos from a space, and I can lift a bunch of properties from spaces through that construction in a way that's probably the best developed aspect of topos theory. And so that gives us a nice vocabulary for talking about various properties. All right, so first of all, sites. The data of a site consists of a small category. I was asking the person sitting opposite me at dinner last night what their favorite small category is, so if you don't have one, then you should choose one. Just to get intuition, and if you're feeling uninspired, then there's an example at the bottom that you could choose that isn't the most interesting, but will serve the purpose. So we have this small category. These are the basic, this is the basic structure on top of which I will build my topos. And associated to that category, I have a Grothendieck coverage. I'm using the word coverage rather than topology here just to avoid confusion later, but I should mention that Grothendieck topology is also used. So I have a Grothendieck coverage on my category, which tells me which collections of arrows cover each given object. So to explain where that terminology comes from, the motivating example of a site is you give me a topological space X. I take the open subsets of X. They form a partially ordered set, which I can view as a category. And then for each for each object in that category, which is an open subset of my space, a covering sieve will be an open cover of that open subset. All right. Now, there are some axioms that I'm omitting here, like what the conditions on the coverage have to be. But what I want you to retain is I have a pair consisting of a category and some extra data. All right. That will be entirely sufficient for the talk. Next up, I should explain how a site produces a topos. So in order to do that, if I just ignore the coverage, then I can construct pre-sheaves on my category. So I can look at contravariant functors into the category of sets. So to each object a set, to each morphism a function, and these form the objects of a category, in which the morphisms are the natural transformations between these functors. Now, pre-sheaves, great, but to be a sheaf, I just have to satisfy some extra conditions which are encoded by my greater than coverage. So the category tells me what pre-sheaves I'm living inside, and the greater than coverage J gives me an extra condition telling me which of those pre-sheaves are valid sheaves. So I get a full subcategory, which is a reflective subcategory of the category of pre-sheaves. Again, that's about the extent of detail that you'll need. All right. On to the second way of viewing toposes. So a special case of the category of pre-sheaves that I just presented is the category of pre-sheaves on a monoid when I view that monoid as a one-object category. Now, I've already talked about monoids a bunch. I'm assuming that everyone knows what a monoid is. But in case you don't remember what an action of a monoid is, it's where I take the underlying set of L, and I take my favorite set X, and then I have a function from X cross L to L, which respects the multiplication in the sense encoded by these two equations. So when I apply alpha to any element X and the unit element of my monoid, I get my element X back. And if I act by one element and then another, then that's the same as acting by the product of the elements. So if you're watching this in the future, do this exercise. All right. So we saw previously that when I have a site, I have this extra data which tells me which objects count as sheaves. So something which turns out to be roughly dual to that is to put a topology on my monoid in this situation. So if I do actually view the objects of my pre-sheaf category as actions, then I can ask about continuity of those actions for this topology. Okay, and this turns out to be another way of building a topos. I told you that the site's way was definitional, so the actual statement of this proposition is that there is some site that I can extract, but this gives us another point of view on these toposes. All right, time for the third point of view, which is going to be the longest of these introductory ones. I have to explain to you all of categorical logic in 10 minutes, so buckle in. First of all, to do anything in logic, we need a signature. We need a language to describe the components of what we're going to be dealing with. So we have sorts, also known as types, but I'm going to use that for a slightly different purpose. So we'll stick with sorts. I've got some relation symbols, I've got some function symbols, and these are all just formal symbols with some associations between them. So each relation symbol has some list of sorts associated to it, which I denote like this, and each function symbol has a list with some special final term of sorts associated to it too. And in spite of the suggestive notation, this is entirely formal. That's the point, right? I eventually want to interpret all of these things, but for now, I'm just building a language. So, given this signature, I also give myself some extra letters to work with. I have some variables, and each variable has a sort associated to it, which I'm going to call its type. So I'm probably going to use this in the few places where I actually give types to my variables. And from variables, I can build terms. Okay. I have my variables. They're an example of terms. And then I can use function symbols to build terms from other terms. And I inductively build up a language of these things. Now I'm going to take a breath here, because while I am attempting to introduce all of logic from scratch, there is a lot of terminology to absorb if you're seeing this for the first time. So in the next slide, I think I have an example of where we're going with this. So out of terms, I now construct formulas. And these express relationships between terms. And while this expression for what a generic atomic formula looks like might be not very informative, the kind of typical example of a formula is an equation. So I have a left-hand side and a right-hand side, which are terms constructed using my function symbols, so the things which eventually will be interpreted as functions, but which for the time being are just formal language. And I have, again, an entirely formal equality symbol, which is relating these two things. Okay. Right. So with this, we've now used up all of the things in our signature to construct atomic formulae. But those aren't really all that we need to express ourselves when we're doing maths formally. We need some way of combining these atomic formulae, and which ways that we permit ourselves to combine them determines which fragment of logic we are working in. So here's a big table, most of which you can ignore. What I want to draw your attention to is this top row, where I have a bunch of different connectives that you could use to combine your symbols. And again, everything's formal. You can probably guess what all of these things will eventually mean, and moreover, what the rules will be for manipulating them. But the main row that I will need for this talk is this row consisting of geometric logic. So in geometric logic, I can build up formulae by possibly starting with true or false, or my atomic formulae that I introduced previously. And then I can take finite conjunctions of them. I can quantify them existentially. I can take finite or even infinite set-indexed disjunctions of them. But note that there are some operations that I am not allowing in this fragment of logic. And I will explain shortly why that is. All right, so I can't do universal quantification. I don't have implication. I also don't have negation by extension. So bear that in mind. So finally, I can tell you what a theory is, as promised in the second slide of the talk. A theory, once you've given me a signature sigma, is just a bunch of axioms, where by axiom I mean a relationship between formulas that I write like this. So phi and psi are formulas here. They're geometric formulas, which means that I built them up using the connectives that I just mentioned. And the intended interpretation of this is not quite as clear as for all of the rest of the ingredients that I've mentioned so far. So I should mention that if you're reading this, what you should be thinking is, for all values of x, if phi of x is true, then I can deduce psi of x. So here's an actual example of a theory in this world. If I am constructing the theory of fields, well, I need my 0, my 1, my addition, my multiplication. Those will be instances of function symbols. I don't really need any relation symbols besides equality. And I have all of my equations which represent the familiar axioms of rings. So commutativity, units, associativity, and note that the way that you would normally present these would typically omit this part, right? I would just say for all x and y, this identity holds, but this is the way of putting this in the format that I presented in the previous slide. And the important thing for us is that we have this extra axiom, and this is the way that you would express either for any element, it's either 0 or it has an inverse. Okay, so hopefully this slide illustrates how the theories for the types of objects that you're familiar with working with in maths generally can be translated into this format. Unfortunately, we're not done with logic yet, because that's all syntax. And I now need to say, when you do want to interpret these, how do you do it? And what makes this categorical logic is, rather than just associating sets to everything necessarily, I can take an arbitrary category, C, and I've constructed my language and everything, I've built everything up in such a way that as long as C has finite limits, say, that's enough to reconstruct all of this. And you could, in fact, go a bit further. You only really need a monoidal product here, for instance, to combine your interpretations of the individual sorts, but we'll be working with categories with finite limits throughout, so let's not overgeneralize things. So finally, this is, I should have said out loud, this is a definition of a sigma structure, which is just an interpretation of all of the ingredients in the signature. And to be a model of a theory, once I've decided what my axioms are, it's saying that if I extend those interpretations to interpretations of all of my formulas, then an axiom should be valid in my sigma structure if I have a relationship between the interpretations of those formulas, which is just containment of sub-objects. There's a lot of text on this slide. What I really want you to take away from it, though, is maybe I should give an example of how this extension works. So, for example, in the previous slide, I gave you, in a sigma structure, an interpretation of a relation as a sub-object of these products of interpretation of sorts. Suppose I have two relations, and I want to take the conjunction of them, and I want to interpret that formula, then I just take the intersection of those sub-objects. And similarly, disjunctions are interpreted with unions. I'm just going to say, and so on from there. The details, in fact, will also be extraneous to the talk, as long as you have some idea of what it means to be a model, possibly from knowledge of model theory external to this talk. All right. I'm doing quite well for time. That's good news. Okay, the final thing I need to do is put this in the context of toposes in two ways. First of all, at the start of the previous slide, I said as long as C has sufficient structure, I don't really need to specify what that sufficient structure is, except to tell you that toposes have that sufficient structure. And in fact, they have enough structure to interpret a lot more stuff, but there is a reason that we restrict ourselves in this way. And so if I take a topos, then I can construct a category of models in that topos, that is all of the possible interpretations of my theory, which validate all the axioms internal to this fixed category F. And I allow all of the homomorphisms between these. And rather than explaining in detail what a sigma structure homomorphism is, I'm going to say that another way of presenting these is to build another category called the syntactic category of my theory, where the objects are formulas, the morphisms are special formulas. So it's entirely built from the data of the theory that I'm starting with. And with this formalism, T models in my topos F correspond exactly to functors which are suitably structure preserving from my syntactic category to F. In other words, I can think of models as functors, and what I called sigma structure homomorphisms correspond to natural transformations. So I'm again reducing everything to functors and natural transformations. And finally, this syntactic category is a category. I can add some data to turn it into a site, and ta-da, I have a topos by the method I introduced earlier. All right. Finally, we have our external point of view, and in order to present that, I need to say what the transformations between toposes are. They're geometric morphisms. They are an adjoint pair of functors, such that the left adjoint is required to preserve finite limits. And there's a reason why they're called geometric morphisms, which is that they are adjunctions. If I take the special case that we saw earlier of sheaves on a space, then I can identify geometric morphisms with maps, continuous maps between spaces. I have to slightly restrict my class of spaces to make that strictly true, but intuitively that's where this comes from. Okay, and so having presented what geometric morphisms are, I can also add some natural transformations between them, which actually go between the inverse image functors. So note that here f and g go from f to e, right? The direction is this way, but if we look back at the previous slide, the inverse image functor f upper star is going the opposite direction, and I'm actually looking at natural transformations between those functors, right? But that convention aside, I have what I'm claiming is a bicategory. So I've got my toposes, I've got my geometric morphisms, and I've got my geometric transformations between them. Yeah?
Just a quick question. So if you had your morphism of subspaces, I think that the F with the star up is going to be like the restriction.
Right.
And the other one, what is it going to be?
It's an extension to Y. So indeed, this is an extension by colimits of the adjunction of partially ordered sets between the opens. So I have the inverse image map on open sets, and that extends by colimits, and then I have the direct image map, which literally sends an open to its image, and that is similarly being extended in such a way as to preserve limits in that case, because it's the right adjoint. All right. So I think we're almost at the end of the introductory section, but this is intentional. I wanted to spend all this time on this. So now that you know that we have a bicategory, it becomes interesting to talk about representable things. And specifically, I want to take my favorite topos E, and I want to consider geometric morphisms into it. And because I'm in a bicategory, this actually gives me a category of such things, because I have not objects which are geometric morphisms, and then I have my natural transformations between these. And as is typical, this is called a representable pseudofunctor. And it's not really that intuitive what one of these should look like. So for instance, if I take the first example of a topos, which is the category of sets, then there is a unique geometric morphism from any other Grothendieck topos. And so this pseudofunctor isn't very interesting. It just sends everything to the one object category up to equivalence. What is interesting is that I already have an example of a pseudofunctor to hand. You remember that I told you if you give me a topos F, then I can give you the category of models of my theory in F. And moreover, the reason that we restricted ourselves to geometric logic is that inverse image functors preserve all of the structure that I use to interpret the connectives in geometric logic, which means that if I take a model of my theory T in F, and I have a geometric morphism into F, then I can transform that model by applying the inverse image functor into something in the domain topos, right? So I end up with something contravariant, and I have this pseudo-functor. And what I want to convey is the fundamental theorem of classifying toposes, which says all of these pseudo-functors, no matter what geometric theory I start with, has a representing object, and moreover, it's the topos that we built earlier from the syntactic site of the category, of the theory, rather. So not only do we have a representing topos for this pseudo-functor, we know how to build one if I'm given an explicit presentation of the theory. All right, quick breather. Any questions so far? Yeah.
You say top is a bi-category. Do you mean it's weak, the composition?
So you can make it straight. The reason I talk about it as a bi-category is because the factorization systems that I'll use, that I'll employ later, are not strict factorization systems. So they're orthogonal up to natural isomorphism. And I mean, I guess moreover, when I specify geometric morphisms, I can specify, say, just the left adjoint, and then the right adjoint is only uniquely defined up to isomorphism. So I'm only doing it to have that flexibility. So even though I've explained to you how to interpret models in arbitrary categories, we're now going to go back to model theory and interpret everything in sets. Don't be too disappointed. So first, special case of geometric morphism is a geometric morphism out of the category of sets, which I mentioned as an example previously. So this stems from the observation that if I have a point of a space, I can identify that with a map from the one-point space into my space X. Change of perspective that I hope you experienced nice and early in your category theory education. But it's very useful when you're trying to transform ideas internal to an object to categorical properties that you can manipulate outside of the object by just looking at the categorical structure. And so this is the definition that we lift. I mean, we can literally lift it in the case of the spaces, because sheaves on this one-point space is equivalent to the category of sets. And so when E is the category of sheaves on a space, these are literally in correspondence with continuous maps on the point. But we generalize this to an arbitrary topos. So, going back to my fundamental theorem of classifying toposes, what this says is that a point of the classifying topos for my theory T corresponds to a model of T in the category of sets. Right? So I can treat models, I can do model theory in the category of points of my topos. And that's exactly what I'm going to do in the rest of the talk. So first, I'm going to specify a property of a geometric morphism. This couldn't really fit earlier in the talk, but it will be relevant shortly. So I mentioned earlier that the category of continuous actions, when I have my monoid L and a topology on it, and I have my subcategory of continuous actions, I actually have a geometric morphism between these two categories, where the inverse image functor is full and faithful. That's the inclusion of the continuous actions into all actions. And this has a bunch of properties. So it's not only full and faithful, it's closed under subobjects and quotients. And the reason that I'm mentioning this explicitly is because there's a result that I proved in my thesis, which says that if I have an arbitrary topos E, and I have a hyperconnected morphism from pre-sheaves on L, we know that these continuous actions are a particular instance of that. But it turns out that I can find a monoid, which is not necessarily the same as L, which presents E as a category of continuous actions. So this property of having a hyperconnected morphism from pre-sheaves on L characterizes toposes of this form. But the monoid that we actually end up with is the monoid of endomorphisms of this point. So I have a geometric morphism from the category of sets, where the inverse image functor here is just the forgetful functor that just gives me the underlying set. And so I can compose these geometric morphisms to get a point of E, and the endomorphisms of that point give me the monoid that I'm looking for. Right? This will explain why I have to do some abstract stuff in a few slides' time. So, if you've fallen asleep, now's the time to wake up, because we're actually getting back to the point of the talk, and things might get a little bit more interesting. So, to summarize what we've got so far, I have my favorite theory, T, over a signature sigma, which I only need around for formal reasons to be able to actually express what the theory is. I've got my favorite model of my favorite theory. Maybe your favorite theory is the theory of groups. Maybe you have a favorite group. Well, here's a geometric morphism for you. Now, already this encodes potentially all of the information about that particular group. But what I want to do is treat it as a geometric morphism in this bicategory. I want to treat it formally as a transformation between toposes and use the tools that I have from topos theory to decompose it and see what further things I can understand about it from the outside. And I'm going to keep flipping between the perspectives I have on toposes to understand what the intermediate ingredients are. So first of all, I'm starting with just M. One of the things I can do is I can take what's called the surjection inclusion factorization of this morphism. So to give specifics, what this does is it tells me the smallest subtopos of my classifying topos through which this geometric morphism factors. So that's formally how it's constructed. From the logical perspective, what this produces is a new classifying topos where I've added to my theory all of the axioms that are valid in this specific model. So, for example, if your favorite group was finite, then we would include all of the axioms that specify how many elements there are. If it's a torsion group, which it would necessarily be if it's finite, then we add axioms for that as well, and so on and so forth. All of the equations which are valid in my model, and all of the relationships between the relations that I can express in geometric logic, I'm adding to my theory to produce this theory of the model T sub M. Okay, now I have a shorter morphism here, this diagonal one, and I'm going to factorize this further, all right? And specifically, I'm going to factor it through a category of actions of a special monoid. So the endomorphisms of my model, if I'm used to thinking of groups, then these are just going to be the group homomorphisms from my group to itself. But those, since the correspondence from earlier is a categorical correspondence, those will correspond to natural transformations on the inverse image of this geometric morphism. To put that in other words, I have the logical point of view that enables me to calculate what this endomorphism monoid is, and it tells me what the endomorphisms of this geometric morphism will be, right? So if I take any object here, or indeed here, it actually makes no difference, and I apply the inverse image functor, well, any such natural transformation has a component of that particular object. If I assemble all of the components at that object of the natural transformations, then I end up with an action of the monoid of natural transformations on the image of this specific object, which means that I can factor this in a canonical way through the category of presheaves on the opposite of that monoid. The takeaway is that I can perform this. This is not just any old monoid, but a specific one associated to the model, namely the opposite of its monoid of endomorphisms. And the reason it has to be the opposite is because pre-sheaves give me right actions, and when I have an endomorphism, it's acting on the left, and if I flip the monoid around, then left and right get swapped also. So just for comparison, I mentioned that this earlier one was a surjection inclusion factorization. So what are the properties of these two? So E turns out to be an essential surjection. This is the morphism whose inverse image is the forgetful functor from earlier. And S is also a surjection. But we'll see another property of it in the next slide. The slide after this one. So, all right, maybe I've been a bit overzealous, and I know that my topos E must classify some theory T, but I don't actually know what that theory looks like in full detail. And I'm really struggling to calculate what my monoid of endomorphisms is. Well, suppose I have a site for my category. One way that I can compute these endomorphisms is by observing that because everything in my category is generated from objects coming from this site, I can just look at what happens on the images of those representable sheaves, and that will entirely determine the endomorphism monoid. And that's what this isomorphism expresses. It says if I take all of the objects in my category and all of the elements which live in S upper star of my category, and I assemble them literally into a category of elements, then the limit of that diagram produces my monoid L. And the way this works is an element of this limit I can think of as a sequence of elements in S star X, indexed by the elements in appearing in my model or appearing in the images of the representable sheaves. And that exactly encodes a function which sends X to whichever element I have chosen in S star of X. Now, okay, being completely honest, this doesn't really help me calculate what the monoid is, but I can exploit this isomorphism to deduce an intrinsic property of S. All right? So it turns out that S has this property of being representably full and faithful on essential geometric morphisms. But I'm not expecting that to be transparent. I'm saying, sure, I have a morphism in my dicategory, I can compose with it, that's going to induce a functor. Moreover, on the left-hand side, if I restrict my attention to essential geometric morphisms, I realize now that I haven't told you what those are ones where not only do I have my adjunction with the inverse image functor preserving finite limits, my inverse image functor actually preserves arbitrary small limits. That is, it has an extra adjoint. But the important thing here is that, in particular, when I take an essential geometric morphism, that inverse image functor will preserve this limit, right? It will preserve whatever is happening at L, and that turns out to mean that any such natural transformation is determined by its restriction to things in the image of S upper star. If that was too hard to follow, what's important here is that I can extract something intrinsic about S, which I can then exploit in a couple more slides' time. Let's go back to this diagram. Let me just see how much time I have left. All right. So now I'm going to further factorize S using the hyperconnected localic factorization. I mentioned earlier what hyperconnected morphisms are, and moreover, what the significance of having a hyperconnected morphism out of pre-sheaves on L is. And we'll come to that soon. But the important thing here is, on the localic side, what a result in the theory of classifying toposes is that if I have a localic geometric morphism into a classifying topos, then I can present the theory classified by E in this case as a theory obtained by just adding relations and axioms to my theory. I don't need to add any sorts is the main thing. So I have a way of extracting a theory classified by E. But in order to really understand what's going on this side, I'm going to exploit the property I just proved about S. So it turns out that this hyperconnected factor H is also representably full and faithful on essential geometric morphisms. And I have an explicit argument in terms of Hom sets here. It's a bit wordy, so I'm going to instead go back to the previous slide, but I guess check out my slides if you want this version. So what I use is a fact about localic morphisms, namely that they are representably faithful for any morphism, which means that if I take natural transformations between things coming into pre-sheaves on L, then I can compose them with H, and then I know that when I compose with L, the result is faithful, and moreover, that when I compose with S, that I end up with a bijection. And so the result is that because composing with S gives me a bijection, I know that this must be a split mono and this must be a split epi. Because L is localic, I know that this is also an injective map. And so this must be a bijection, which forces this to be a bijection, which is just what I need, all right? And the significance of that is that, if you recall, this is an essential surjection. It's an essential geometric morphism. One thing I haven't told you about it is that its endomorphism monoid coincides with the opposite of L. In other words, because H is full and faithful on essential geometric morphisms, the conclusion I can draw is that the endomorphism monoid of this point coincides with L. I don't end up with a new monoid, I just keep the monoid that I've already constructed. So that is the result that I will explain here. But there's a few ingredients missing to like, I haven't actually told you what this theory is, I haven't actually told you what this topology is, and that's kind of the second thing is the thing I promised at the start of the talk. So let me rush through those, as I'm sure you're feeling very energetic and following everything that I've said very attentively. This shouldn't be a problem. So which relations do I actually add? It turns out that I can just add the equivariant ones, the ones which are respected by the action of L. That is the content of this paragraph. On the other side, which topology do I add? Well, it's the one determined by looking at finitely many elements of my model, right? Whatever ingredients I've included in my model, those will give me sets, and I'm taking as basis of my topology on my monoid L, all of the elements which coincide with a given one on some finite number of elements of M. Now I could have simplified this because each of these is an intersection of things where I just take k equal to 1. And it turns out I can actually use that to prove that this is exactly the topology that I get out of the framework for my thesis that I mentioned earlier. So we really get the topology, which is the same one that Hodges used in the result that I quoted at the start of the talk, out of this correspondence. All right. So, last thing, I believe I have about 2 minutes. Yeah, perfect. So if I present the Galois correspondence that I described at the start in terms of these diagrams, so I have my model M, I have the theory of the model, I'm still taking this surjection inclusion factorization. What I can do is I can add some relations to my monoid, to my model rather, and I can take the theory of the resulting model. And another way of seeing this is I can add, the reason it's grayed out is because I don't really need it, but I can just add relations to my theory directly, equipped with an interpretation over my specific model, and I can factorize it this way instead. And now, if I factorize both of these morphisms in the way that I described previously, I end up with this diagram. And here I'm highlighting the right-hand side of the correspondence. So I can look at the family of all relations which are preserved by my monoid, and the family of all further relations on my relational extension of n, which are, sorry, all of the elements of that monoid which preserve all of the relations I've added, and I end up with necessarily a submonoid, right? Because I've only added relations here. And I guess the thing I want to close on is, if we examine the square, I haven't given the background results to back this up, so you'll just have to take my word for it. I told you that if I have a localic morphism, then I can express the theory that results by just adding relations. The converse is also true. If I'm only adding relations, then the comparison morphism here is localic. And so going over to the other side of the correspondence and viewing these as toposes of continuous actions for some topologies on these respective monoids, it turns out that being localic corresponds exactly to this inclusion being a closed inclusion of monoids once I've added the topologies. So we do actually get the topological aspects not only with the topology being recovered, but the closure condition being identified. And we can go the other way, but the picture doesn't fit together quite as nicely because I need to do the restriction of the topology, and I end up with the fully extended model up here. But I already presented to you how this Galois correspondence would work. All right, and that's back to the result that I presented at the start. Thank you very much.
Any questions for Morgan?
Yep.
So with the localic expansions, it isn't the case, right, that every localic the localic expansion you take isn't unique on the theory,
right?
Given the localic geometric morphism.
Mm-hmm.
So it means that the theories that you're getting using this method, you're only going to get a bijection between the closed submonoids and the relational extensions up to Morita equivalence, right?
Yes. Let me see, would it actually be up to Morita equivalence? Yes, I think so. Yes.
And so is this also reflected in the classical model theory case within Hodges?
Yes, in the sense that the class of relations that he takes in one direction is not a canonical choice, but it is sufficiently maximal, right? So indeed, you could prove that any alternative choice would be Morita equivalent.
So like a reflective adjunction going on where there's this canonical expansion. Okay, cool.
Yeah. Yeah, like, you didn't need all of the topos theory I gave to understand this correspondence because you can just do it directly. So I guess the point of the topos theory is it gives a nice topos theory result, but also it explains where these ingredients actually come from. Anyone want to know about the group stuff? Yep.
Yes, at some point you had a geometric, you take the geometric surjection part of the factorization of the model, and you get something which is essential, an essential surjection and a surjection that is representatively pretty faithful.
Mm-hmm.
Do you think this is a factorization you can generalize to arbitrary geometric surjection, or is it specific to the fact to look at the model which is simple?
So I have thought about that. The issue is that the result about S really relies on this, that is, preservation of this particular limit, which means that I don't expect this result to hold for generic geometric morphisms. I don't know. I started looking for a counterexample, and then it took me too far outside of the paper that I was writing, so I just left it for the future. I mean, I should note that if I take a finite model, then I can typically very strongly constrain the size of this limit. So the smaller the model and the smaller the theory, the closer I get to being exactly full and faithful. And I think you could probably get some orthogonality as long as you had a slightly stronger condition. But I wasn't able to get the ideal result that you're suggesting. All right. Yep.
Thank you for the talk. Could you maybe expand a bit on why geometric logic is the correct setting to?
Right. Okay. So I did mention that you can interpret more than geometric logic and toposes, and really the motivation for doing this is the result on classifying toposes that I mentioned. So the fact that inverse images of geometric morphisms preserve all of the ingredients of geometric logic, but by no means anything else. Like you can find counterexamples to any of the other logical connectors having their interpretation preserved. And so as soon as you are working in the bi-category of toposes and geometric morphisms, geometric logic is the largest fragment that you can hope to study using these representable methods. But you can do better. Like you can constrain which morphisms you use. Like if you take open geometric morphisms, then universal quantification is preserved by the inverse images as well. And you can go even further and look at logical morphisms. But what you lose in doing that is the ability to use all these different perspectives, because none of the morphisms that I worked with today had those stronger properties, besides hyperconnected morphisms being open. So, for the future viewer who would have asked this, what happens with groups is I can no longer say that this intermediate thing is representably full and faithful on essential geometric morphisms, because we already know that there aren't enough endomorphisms here for that to be true. But we could hope that it's representably faithful and full on isomorphisms. So this is called being pseudomonic. And on the other hand, because the correspondence that I presented was between submonoids and therefore not necessarily subgroups, in order to constrain the other side to get a correspondence between closed subgroups and something else, I think you'd need to restrict to decidable relations. That is, where you not only add relations to your theory, you add the complements of relations. But I haven't been able to verify any of this yet.
Okay, thank you. Let's think as figured yet.